Alright, here we have the homework from section Beta 1. This is homework Beta 1a. Directions for the first three problems. Find the coordinates of P prime if P and P prime are symmetric with respect to point M. I would encourage you to draw a segment. I'm going to put it right underneath here. So here's where P is. Here's where M is. Over here, this little guy right here, that's P prime. P we'll call x sub 1, y sub 1. P prime we'll call x sub 2, y sub 2. So we use the midpoint formula, where you take the average of your x values followed by the average of your y values. Our midpoint, we know, is the ordered pair 1, 1. Keep in mind, midpoint means it breaks the segment into two equal parts. So our midpoint is 1, 1. Our x sub 1 is negative 2. X sub 2, we don't know. Y sub 1 is negative 2. Y sub 2, we don't know. Then we can say, well, this 1 and this fraction, those are two things talking about the same thing, so let's set them equal to each other. If you solve that, you multiply both sides by 2 and get 2 equals negative 2 plus x sub 2. If you then add 2 to both sides, you get 4. Looking at the other one, it's equal to this fraction. So that's 1 equals negative 2 plus y sub 2 over 2. Multiply both sides by 2, then add 2 to both sides, and you get y sub 2 is 4. I got a little bit big here. Just going to bring this over just a nubbin. Just a nubbin. So my answer, what's the coordinates for P prime? P prime is 4, 4. Question 2, same concept, different numbers. We have P, M, and P prime all in the same segment. M is the midpoint. We don't know what P prime is. Using the midpoint formula, capital M is the average of the x values and the average of the y values. We know what the midpoint is. It's 0, 0. And this guy's happy. Yay! Our x value, one of our x values is negative 3. The other one we don't know. So we'll say it's x sub 2. One of our y values is 2. The other one we don't know. So we'll call it y sub 2. Just like the other one, we set 0, the first part of this ordered pair equal to the first part of the second ordered pair, and the second parts are equal to each other. So we get 0 equals negative 3 plus x sub 2 over 2, and we get 0 equals 2 plus y sub 2 over 2. We multiply both sides by 2 here. 0 times 2 is 2. Add 3 to both sides, and you get x sub 2 is 3. Here if you multiply both sides by 2, then subtract 2 from both sides, you get y sub 2 is negative 2. So for this problem, the coordinates of P prime, x, y, 3, negative 2. Third problem in this group. Same situation. Just more practice. Midpoint is equal to the sum of the x values divided by 2, and then the sum of the y values divided by 2. Our midpoint is -3, 1. One of our endpoints has an x value of -3. The other endpoint, we don't know its x value. One of our endpoints has a y value of 7. The other one, we don't know its y value. So, set -3 equal to the first part, and we set 1 equal to the second part, which is going to give us a -3 equals the sum of -3 and x over 2, and 1 equals the sum of 7 and y divided by 2. If we solve each of these, -3 times 2, that's a -6. If we add 3 to both sides, we get -3 for x sub 2. This other equation, if we multiply both sides by 2, then if we subtract 7, we get -5. So p prime for this problem is -3, -5. Question 4 and 5 are supposed to determine if the function's even, odd, or neither. To determine if it's even is to determine if it's symmetric with respect to the y-axis. To determine that, you change the sign of x and you leave y the same. To determine if it's odd, that's to say if it's symmetric with respect to the origin. To see if that's true, you make the x negative and you make the y negative. Making it negative means to change its sign. It doesn't mean to make everything a negative number. So let's try even. Got our function here. It appears as though I am missing something in my function. Hold on a second. For some reason the subtraction is gone, as it is over here. Anyhow, to see if it's even, we take our y and leave it the same. We take our x and we change the sign. Simplify it. Negative x to the third is going to give us a x to the third that's negative. And you take that negative times a positive 6 and you get -6x cubed. Subtracting 3 times a negative x is going to give us a plus 3x. We bring down the 5. Is that the same as the original? No. This problem is not even. So is it odd? Here I change the signs of my x's and my y's. So it's going to be a negative y equals 6 times a negative x cubed minus 3 times a negative x plus 5. So it's a negative y equals negative x to the third is a negative x cubed. That times 6 is a negative 6x cubed. Subtract 3 times a negative x is a plus 3x, and then bring down the plus 5. Get y by itself, divide each term by -1, or multiply each term by -1, either way. And you get this. Not the same as the original because of the subtract 5 instead of a plus. So this problem is neither. Number 5, let's see if I can organize my work a little bit better here for number 5. Is it even? Is it symmetric with respect to the y-axis? Well, we're going to take y equals 6 minus 6, and instead of an x, we write a negative x squared, plus negative x squared. A negative x quantity squared is a positive x squared. A minus 6 times a positive x squared is a subtract 6x squared. A negative x to the second is positive. Adding a positive is the same thing as, well, adding a positive. Is that the same as the original? Oh, I made a mistake, ladies and gentlemen. This is supposed to be an 8 for an exponent, not a 2. Negative 8, negative x to the 8th is going to be positive x to the 8th. Is that the same as the original? It sure is. This function is even. Is it odd? Change the sign of x and y to see if it's odd. So we get negative y equals 6 minus 6 times negative x squared plus negative x to the 8th. Simplifying this, getting y by itself, you're going to find that it's not odd. So, number 4, neither. Number 5, odd. Number 6. Even, symmetric with the y-axis. So replace our x's with negative. And we simplify it. Negative x to the 9th would be an x to the 9th negative. Negative times a negative is a positive, so it's 3x to the 9th. Negative x to the 5th is an x to the 5th negative. Negative times a plus 4 is going to be a subtract 4x to the 5th. Is that the same as the original? No. This function's not even. Is it odd? To determine that, it's symmetric with the origin, and make x and y a different sign. So it's negative y equals negative 3 times a negative x to the 9th plus a 4 times a negative x to the 5th. It's going to give us a negative y equals a negative x to the 9th is an x to the 9th negative. Negative times a negative is a positive. Negative x to the 5th is a negative. Positive times a negative is a negative. I already wrote the plus sign, so I'll say plus a negative 4x to the 5th. To get y by itself, multiply each term by a negative 1, and you get y equals a negative 3x to the 9th plus 4x to the 5th. Same as the original. Therefore, this function is very, very odd. Funny, wasn't it? Next. The graphs below are portions of complete graphs. Sketch a complete graph for each of the following symmetries. A, with respect to the x-axis. So here is the x-axis. If it is symmetric with respect to that, it is going to look like this. Be the same angle between the line of symmetry and each ray. So that is part A. Part B, the y-axis. Well, here's the y-axis. So whatever angle it is between the original ray and the y-axis, it's that same angle on the other side. So your ray is going to look a little something like this. This is part B. Part C, the line y equals x. Draw that line. Line y equals x has a slope of 1 and a y-intercept of 0. Therefore, if this light blue arc is my original, the measurement from here to that is going to be the same on the other side. So it's going to look a little something like this. That is part C, I believe. Then part D, I got a lot of stuff on this picture, perhaps too much. The line y equals a negative x. That looks something like this. So the angle from here to here should be the same angle. So it's going to look perhaps like this. This is the line y equals negative x. And this is part D. Question 8, it's a different graph, but it's the same question. With respect to the x-axis is the first one. Well, here's the x-axis. So this curve that comes up like this is, if you have a mirror image, it would be down something like this. Not perfect, but that general concept. It's part A. B, the y-axis. Well, here's the y-axis. So this blue curve that's reflected over the y-axis is going to be over here like this. See the line y equals x. If you flip this, it's going to be flipped like this. And then the line y equals negative x. This one gets a little fanciful. I didn't label this to C. It is going to be, let's see, this is our original. And if it's reflected over this line, it's going to look like this. That's part D. Number 9, reflected over the x-axis. It's going to be like this. Reflected over the the y-axis. It's going to be like so. This is B, this is A. The line y equals x, which is this line here. It's is going to be down here. And then finally, the line y equals negative x it's just tracing over what's already there. This yellow part is going to flip up and be where the green part is. The green part's going to flip and be down where the yellow part is. Number 10, I think the first one is the x-axis. So if this is flipped over, it would be like so. Part B is the y-axis. That would flip it over like so. The line y equals x be like this. And once again, how do we know this? Well, if you get stuck, this is what I would do. Take a point, take that point so that it hits your line of symmetry at a 90-degree angle. Extend that in the same direction, the same length, and see where it hits. That point is on your graph. And finally, we have the line y equals negative x, which is going to look like this. Number 11, over the x-axis is going to be like so. Over the y-axis, it'll be like so. Over the line y equals x would be down here. You have a circle at this point. And then the line y equals negative x, this blue curve is reflected on itself. Once again, the gray part would move up to where the white part is, and the white part would move over to where the gray part is. Number 12, part A over the x-axis would be down like so. Over the y-axis, over the line y equals x, doesn't change. Left comes down here and the right comes up there. I didn't label this very well. Previous problem. And then the line y equals negative x, if you reflect this blue over that, it's going to come down here. You're supposed to figure out which of these things this graph is symmetric to. So the x-axis, for example. Leave x how it is. Change y to a negative. If we do that here, nothing on the right changes, getting y by itself. We get this. Not the same as the original. Therefore, this is not symmetric with respect to the x-axis. So the y-axis, change the sign of x, leave y the same. So we get y equals 6 times a negative x to the 4th minus 3 times a negative x squared plus 1. A negative to an even power is going to be positive. A negative to an even power is going to be positive. So you get a subtract 3 times a positive x squared is a subtract 3x squared. That's the same as the original. So it is symmetric with respect to the y-axis. I forgot the origin. It was the first thing we were supposed to check. For the origin, you change the sign of x and y. So negative y equals 6 times a negative x to the fourth minus 3 times a negative x squared plus 1. It's going to give us a negative y squared equals 6x to the fourth minus 3x squared plus 1. Getting y by itself, we'll see this is not the same as the original. So it's not symmetric with respect to the origin. Align y equals x. Put y in for x and x in for y. You'll see here that not only is it the same as the original, but I can't even figure out how to get y by itself. That's how the original one was. So we'll say no to that. On a similar note, we're going to say no to this next one for the same reason. I'm not even able to get y by itself, which is a little embarrassing. So this graph is only symmetric with respect to the y-axis. Looks like I'm missing a symbol here for some reason. Missing a minus. So let's do the origin first, although it doesn't matter. Just changing your signs for x and y. You got to be careful when you do this that you do order of operations correct. Exponents before multiplication. Negative x to the ninth is going to be negative. Positive 2 times a negative is a negative. Negative x squared is going to be positive. Positive times a negative 7 is going to be negative. Get y by itself. Is that the same as the original? Absolutely not. How about the y-axis? We're doing this in random order. Let's do x-axis so it's not in random order. Leave x the same, change y to a negative. So if we do that for this problem, you'll see it doesn't work. When you get y by itself, everything on the right side has the wrong sign. So it's definitely not the same as the original. The y-axis, you change the sign of x and you leave y alone. Leave her alone there for y. Sorry for blowing your eardrum out there. And yet, I'm not sorry. A negative x to the ninth is going to be negative. Negative times a positive 2 is a negative. Negative x squared is positive. Positive times a subtract 7 is a subtract 7x squared. Not the same as the original. Sign's different in the front. The line y equals x, we make y x and x y. This is one of those problems, once again, that I don't even have any idea how to get y by itself. Therefore, it can't be the same as the original. y equals negative x, I'm going to put a negative y in for x and a negative x in for y. It's going to have the same result as the previous problem, but I still need to do it. You need to show what it is that you can show. If nothing else, it's good mental exercise. So you can see here this is not the same as the original. Therefore this graph is symmetric with none business. It's not symmetric with any of these lines of symmetry. Number 15, you could get y by itself here and then proceed with the problem. You don't need to. I'm not going to. Origin, switch the signs of x and y. Squaring a negative is a positive, squaring a negative is a positive. This is the same as the original. So this is symmetric with respect to the origin. The x-axis, x stays the same, y changes sign. Hopefully you can see what's happening here. This is going to work as well. Because the only thing we change is this y, and it's going to be squared, which is going to make it positive again. Same as the original. About the y-axis. For the y-axis, we change the sign of x, we leave y the same. Hopefully, your little mind, you're seeing this is going to work as well. The only thing we're changing is this x right here, and it is being squared, so it's going to return it to its original pristine condition. Untainted. It lacks taint. It's not tainted at all. Origin, x-axis, y-axis. What's left? We got the line y equals x. Replace y for x and x for y. This is definitely not going to work. Even though I know it's not going to work, and I'm sure you know it too, I can get y by itself, therefore I'm going to. I'm going to add 4 to both sides. I'm going to multiply both sides by 9/4. It's the same thing as dividing, pardon me, it's the same thing as dividing by 4/9. It's the reciprocal of this. It's going to give me 9/4 x squared. 9/4 times 4, the 4's are going to cancel and you get 9. Square root both sides, you get y by itself. You get this very hot mess, which you can see is not the same as the original, but y's by itself, so we know for sure. So, it doesn't work. Finally, you have y equals a negative x. Put a negative y in for x and a negative x in for y. This is not going to work either. In fact, after the first step, the work's identical to what we just did on the line, the symmetry of y equals x. We're still going to show it. It's because we're that awesome. And add 4 to both sides. A negative x squared is a positive x squared. I add 4 to both sides. Negative y squared is positive y squared. I'm going to multiply both sides by 9/4. That's going to give me 9/4 x squared plus 9, because the 4's cancel. When you multiply 4 times 9/4, the 4's cancel. I think I wrote down, I did, right here I wrote down 4y to the 9th. That is poppycock. Should be 4y squared. Please forgive me. Square root both sides. We get this once again, which is not the same as the original. Make sure your radical sign does not extend further than it's permitted to. So no for that last one. 15 is symmetric with the origin, x-axis, and y-axis. Use your calculator to graph the function and determine any lines of symmetry. If you were to use your calculator to graph this, here's what you would get. You would get pretty potentially cool looking, depending on how much of a nerd you are. I am quite the nerd. Something like this. I have my window set -5 to 5 on both the x and y axis. That's what gives me a good view of what this looks like. Any lines of symmetry? Well, we can see it's symmetric with the y axis. Which is also known as the line y equals 0. I'm sorry, x equals 0. The x-axis, definitely not. There's some above, but not below. If it's a mirror image, you'd see the same thing below. The line y equals x, is it the same on both sides? Definitely not. The line y equals -x, the same on both sides? Definitely not. And that's it. I mean, there's infinite possibilities of what it could be symmetric to, but you can see by looking at it, the only way you can fold this in half so that it's equal on both sides is on the y-axis. Plot points to graph the parabola whose equation is this, and a circle whose equation is this. One of the points of intersection of these two graphs is at 2, 0. Do you expect another point of intersection at -2, 0? Why or why not? Well, we're going to learn later, I think in the next section, how to graph this parabola well. Plotting points to graph it is just a pain in the tush. The circle, if you remember anything about circles, I hope that you do, the general form of a circle is like so, where HK is the center of the circle and R is the radius. Therefore, for this problem, the circle has a center of +2, +4, and a radius of plus or minus 16, but a radius is positive, so the radius is 4. So that part's pretty simple, in my opinion, but then again, I get paid to do this, so it should be simple for me. So the center is 2 to the right and up 4. It's a circle. Whose radius is 4. It's going to look something like that. Then we have this parabola. It says one point of intersection between the parabola and this circle is the ordered pair 2, 0. If we were going to graph this like the directions say to, one thing we know for sure, the y-intercept is -4. If I put 0 in for these x's, the first two terms cancel. We know another point of this parabola, it goes through 2, 0. And once again, this is a pain to graph this if you don't know how to graph it. We haven't talked about it yet. It's going to look something like this. This is not perfectly to scale. Something like that. But you're probably thinking, send me mixed messages here. Can I graph it? Can I graph it? You can plot points to graph it, but for a parabola, in my opinion, that's pretty tough to do. So for right now, forget about knowing how to graph it. Throw it in your calculator, you'll see what it is. Even if you had nothing graphed, the question is, do you expect another point of intersection to be at -2, 0? Why or why not? Let me tell you why or why not. Let's talk about some different symmetries. Notice the 2, 0 and the -2, 0. What's different is the sign of the x has changed. So what was xy has now become -xy. It's also possible that the 0 changed sign, theoretically. It could have been that xy became -x, -y. We wouldn't know because if you change the sign to 0, it doesn't appear to have changed. This first scenario is symmetric with respect to the y-axis. The second scenario is symmetric with respect to the origin. Therefore, if we look at either of these graphs, the equations I should say, and check and see if they are symmetric with respect to the y-axis and the origin. If they both are symmetric with either one of those things, either one, then we would expect -2, 0 to be a point of intersection. If neither of these graphs are symmetric to either of these things, then we would say, no way, don't expect it at all. So let's just check. Let's check the y-axis. So we got -y, pardon me, we got +y. Right now I'm doing this one here. We got y equals 3 times a -x squared minus 4 times a -x minus 4. It's going to give me 3x squared plus 4x minus 4. Doesn't work. This graph is not symmetric with respect to the y-axis. Well, let's check the origin, see if that works. So we change the signs of x's and y's for this. And we can see that it is also not symmetric with respect to the origin. So if it's not symmetric with respect to either of them, even if the other one is, we would not expect this point to occur in the other intersection. So you can just write down that last sentence that I said after you've shown this work. Number 18, the light pattern from a fog light at the airport can be modeled by this equation. One of the coordinates of the graph is at 3, 4.5, and one of the x-intercepts is -2. Find the coordinates of 3 additional points on the graph and the other x-intercept. There's 1,001 ways to do this, but we're talking about symmetry right now. So let's use symmetry. If you look at this, each x value and each y value are squared. What that means is if we change the sign of x or y, it's still going to be positive, because when you square a negative, you get a positive. Therefore, we would expect this graph to be even, because it's going to be symmetric with respect to the y-axis. We'll prove that here shortly. We would also expect this graph to be symmetric to the x-axis, so you're just changing a sign. We would also expect it to be symmetric with respect to the origin, because you're just changing both signs. So let me just prove this. For the y-axis, I change the sign of x. And I get that it's the same as the original. So yes, it's even. For the x-axis, you change the sign of y. But you're just going to square it. So it's going to return it to its original pristine condition. So it's symmetric with respect to the x-axis. The origin, well, you change the sign of x and you change the sign of y. Change them both. But you're squaring them both. So it just goes back to the original. Now, once you have that done, and we now do have that done, how can you use this to find other points? Well, if it's symmetric with respect to the y-axis, that means I can just change the sign of the x value. So this point 3, 4.5, if I change the sign of the x value, it's negative 3, 4.5. That point must be on my graph. My x-intercept was negative 2. If I change the sign of the x value, it's positive 2. That's my other x-intercept. For the x-axis, I change the sign of y. So instead of being 4.5, I change it to negative 4.5. This x-intercept, negative 2, 0, if I change the sign of the 0, it's still the same point, negative 2, 0. For the origin, I change the sign of both. So the original was 3, 4.5, so it's negative 3 and negative 4.5. Once again, if I change both signs for the x-intercept, it's going to give me 2, 0, which I already have listed. Find the coordinates of 3 additional points on the graph and the other x-intercept. Well, ladies and gentlemen, we have done that.